Chapter 9 continued. Models of chemical bonding. Section 9.4. Bond energy and chemical change. The relative strength of the bonds in reactants and products determine whether heat is released or absorbed in a chemical reaction. The heat released or absorbed during a chemical change is due to the differences between the bond energies of the reactants and the products as shown by the equation given in the box on this slide. We can use average bond energies to estimate the enthalpies of reactions in which bonds are broken and bonds are made. This procedure will allow us to estimate quickly whether a reaction of interest will be endothermic, delta H will be greater than 0, or exothermic, delta H will be less than 0. And we can do this even if all the average bond energies are not known. Our strategy for estimating the enthalpy of a reaction is nothing more than an application of Hess's law. Remember Hess's law from chapter 6? We will use the fact that all bond breaking is an endothermic process and all bond making is an exothermic process. To use Hess's law, we are going to imagine that the reaction takes place in 2 steps. In step 1, we supply enough energy to break all the bonds in the reactants. In this step, the enthalpy of the system is increased by the sum of the bond energies that were broken. In step 2, we form all of the bonds for all of the products. This step releases energy and therefore lowers the enthalpy of the system by the sum of the bond energies of the bonds that are formed. The enthalpy of the reaction, or delta H reaction, is estimated as the sum of the enthalpies of the bonds broken minus the sum of the enthalpies of the bonds formed as shown on this slide. The minus sign is needed because all bond energies are positive values. The reaction shown on this slide is the formation of hydrogen fluoride from its elements, hydrogen gas shown in blue and fluoride gas shown in yellow. The left hand of the slide shows the breaking of the hydrogen-hydrogen bonds and the fluorine-fluorine bonds. Since bond breaking is an endothermic process, the energy of the system is increased. When the bonds reform by making new bonds, in this case a hydrogen-fluorine bond, energy is released. Delta H for the reaction is equal the sum of the energies for breaking the bonds minus the sum of the energies for making the bonds. When the total bond energy of the products is greater than that of the reactants, more energy is released than absorbed, and the reaction is exothermic. For an exothermic reaction, delta H will be negative. When the total bond energies of the products is less than the total energies of the reactants, more energy is absorbed than released, and the reaction is endothermic, and delta H will be positive. Let's consider the combustion reaction of methane in the presence of air to produce carbon dioxide and water. Remember back in chapter 6, we determined the enthalpy of the combustion of methane to be 802 kilojoules using calorimetry. Let's see what it is using the bond energies in Hess's law. This figure shows that we need to break all 4 carbon-hydrogen bonds and both of the oxygen-oxygen double bonds. 4 times the bond energy for the carbon-hydrogen bond is 1,652, and 2 times the bond energy for the oxygen-oxygen double bond is 996 kilojoules. Therefore, the total energy for breaking all the bonds in the reactants is 2,648 kilojoules. Now we need to make the bonds in our products. Water has 2 hydrogen-oxygen bonds, and we made 2 molecules of water for a total of 4 oxygen-hydrogen bonds. Do you see this? 4 times the bond energy for the oxygen-hydrogen bond is 1,868 kilojoules, which is equal to the amount of energy released when these bonds are formed. Carbon dioxide, which is the other product, contains 2 carbon-oxygen double bonds. The energy released when carbon dioxide is formed is 2 times the bond energy for the carbon-oxygen double bond, or 1,598 kilojoules. Now we plug these values into our equation for the enthalpy of the reaction, where we subtract the energy associated with bond making from the energy associated with bond breaking and find delta H for the combustion of methane to be negative 818 kilojoules. Remember, a negative value for delta H implies the combustion of methane is exothermic. Notice our calculated reaction enthalpy value for the combustion of methane using bond energies is close to the enthalpy value determined using calorimetry, but not exact. Remember that the bond energies are also an average value obtained from many different compounds, which can be used to explain our differences in enthalpy values for the same reaction. This sample problem wants us to calculate delta H of reaction for the formation of chloroform from methane and chlorine gas. To solve this problem, we need to use the bond energies and the equation that we have discussed earlier that are found in your book and on previous slides. So what is our plan to solve this problem and others like it? Remember, we have to break all the bonds in the reactants and make all the bonds in the product. Take the number of bonds either broken or made and multiply it by its bond energy. Add up all the energy associated with the bond making and add up all the energy associated with bond making and subtract the energy associated for bond making from the energy associated with bond breaking. Please try to work through this problem on your own before moving on to the next slide where you can check your work. Notice we need to break 4 carbon-hydrogen bonds and we need to break 3 chlorine-chlorine bonds. Notice we need to make 3 carbon-chlorine bonds, 1 carbon-hydrogen bond, and 3 hydrogen-chlorine bonds. The total energy associated with bond breaking is found by taking 4 moles times 413 kilojoules per mole and add this to 3 moles times 243 kilojoules per mole for a total of 2381 kilojoules. The total energy associated with bond making is 3 moles times 339 kilojoules per mole, and add this to 1 mole times 413 kilojoules per mole, and add this to 3 moles times 427 kilojoules per mole for a total of 2711 kilojoules. Now plug these values into equation 9.2 and solve for delta H of the reaction. Hopefully you found this reaction is exothermic and the total energy released is 330 kilojoules. Now work through the follow-up problem before moving on to the next slide. Please be sure to contact me if you are having any questions or concerns. This is figure 9.19 and it provides us with the relative bond strength and energy from fuels. Couple points of interest here. First, weaker bonds tend to be less stable and more reactive and are easier to break than stronger bonds, which are more stable and less reactive because they are already higher in energy. Secondly, fuels with more weak bonds yield more energy than fuels with fewer weak bonds. Therefore, hydrocarbons that are compounds that contain only hydrogen and carbon atoms will release more energy than carbohydrates that contain carbon, hydrogen, and oxygen atoms. Bottom line is this: a fuel with fewer bonds to oxygen releases more energy. This is table 9.4 and it provides us with the heat of combustion values for some common carbon-containing compounds. Carbon-containing compounds such as carbohydrates and fats are used by mammals for fueling the cellular activities that take place in our bodies. As we digest these foods, similar to combustion, energy is released. Both fats and carbohydrates are considered to be high-energy foods. Carbohydrates are used for short-term release of energy, while fats are used for long-term storage. Fats contain more calories per gram than carbohydrates do because fats have weaker bonds. Fats release more energy per gram than carbohydrates do, which can be seen on this slide.